Okay, back to the solutions to the two problems we left with. The first one, we're given the acceleration of gravity, or little g's value, on the surface of Mars, and we're told that it's 0.38 of what it is on Earth, or 0.38 of times 0.98. And we're told the radius of Mars, and we're asked to determine the mass of Mars. Now here you kind of have to hold your breath and say, well, what do we know? What do we want to know, and what relationship might tell us, something that involves the mass of Mars? Well, what involves the mass of Mars is Newton's law of gravity. So if we write that down on the right-hand side here, we have the force that's on a mass of mass m is g times the mass of Mars, I'm writing that as mm, times little m, the mass of the object, divided by, and here I'm imagining the object is at the surface of Mars, the radius is equal to 3,400 times 10 to the 3, 3,400 kilometers, right, squared. And so that's one way of calculating the force on an object in free fall at the surface of Mars. Then we can use the good old-fashioned method and calculate the same thing. We said the gravitational force on an object in free fall is just the mass of the object, little m, times little g at that location. And the first thing to notice is the little m's cancel out the mass of the object. In other words, both sides are proportional to the mass of the object. But the important thing to look at is that we know the value of little g at the surface of Mars. We know, of course, capital G and the radius, and so the mass of Mars is the only thing that we don't know. So when we set this equal to 0.38 times 9.8, because the little m's canceled out, and so we're after canceling the little m, that should be equal to little g's value, which is 0.38 times 9.8 in SI units. Solving for the mass of Mars, we get 6.454 times 10 to the 23rd kilograms. I suppose we could look it up and see if that agrees with the accepted value. Second problem, a hypothetical planet has a mass 2.8 times that of Earth, but the same radius. What is g near its surface? So it's same radius, but a larger mass. We would expect little g to be bigger, so that's a good cross-check. How do we calculate what little g is? Well, again, the same relationship. We calculate the force on an object, the gravitational force, the old way and the new way. And when we do that, after canceling the mass of the object, we get little g on the planet is capital G times the mass of this planet, which is 2.8 times the mass of Earth, divided by the radius of the planet squared, but we're told that's the same as the radius of Earth squared. And we can throw all that in and calculate little g on the planet, and it indeed is bigger than 9.8, 27.5 meters per second squared. Okay, let's now turn to answering a couple more questions about orbits and objects in orbits around other large masses. The first question is, how fast, and we'll call it v, does an object have to be moving in order to be in a circular orbit of radius r around Earth? Or we'll find out once we get our formula, we can do it around any other mass object. Okay, so we're moving at speed v, radius r, a distance away from some planet of known mass or star of known mass. And the way to do it is, well, we really only have one tool to deal with. We know how to calculate the gravitational force on this object, and we know what its acceleration is because it's in uniform circular motion. If we're assuming it's in a circular orbit of radius r, everything's sort of staying the same except the direction it's moving as it goes around. So the acceleration is the same everywhere. It's v squared over r. So I'm going to turn this picture, sometimes I draw a separate free body diagram, but here I'm just going to turn part of my cartoon into a free body diagram because it's so simple. There's only one force on this object of mass m in an orbit of radius r, and that is the Earth's gravitational force. I just called it F, the force from Earth on that object of mass m. And I chose, as always, some axes. In this case, I know this object is accelerating towards Earth. It's in uniform circular motion, so I chose plus x to be toward Earth. And now I'm going to write down the sum of the force x components equals m times ax. The left-hand side is just Newton's law of gravitation. G times the mass of the Earth, times the mass of the object, divided by the radius of the orbit squared. And the other side is the max, and ax is nothing but v squared over r because we chose plus x to be toward the center of the circle. So that's m times ax, and that's equal to v squared over r. All right, we've got an equation. We can cancel some things. The m's cancel out, but also if I multiply right side and left side by r, the r cancels out over here from the denominator, and 1 power of the r cancels on the left-hand side. We're still left with 1 power of r, the denominator, on the left-hand side. But all that's left on the right-hand side is v squared, and then I can simply take the square root of both sides to get the speed that's required is capital G times the mass of Earth divided by the radius of the orbit. And in this case, you can see, well, if I were in an orbit of radius r around some other planet or star, I would just use the mass of that object. So this is a perfectly general formula for all circular orbits. Okay, next question. What would happen, suppose I have an object in such a circular orbit, and then I put my finger in front of it and I slow it down a little bit. So it's still moving in the direction shown here, but I just cause it to move slightly slower by slowing it down with my hand. What would happen in that case? It's still at the same radius, that same distance r from the center of the planet, but it's not going at this speed anymore. It's going at a slower speed. Seems like there's some sort of contradiction there, but there's not. It's just not necessarily in uniform circular motion anymore. You can imagine if you're not going fast enough, compared to the pull, the gravitational pull of Earth, you're not going to go out far enough to sort of, as you're accelerating toward the Earth, you're not moving fast enough to the side to avoid falling closer to the Earth. So what happens is this object will now start falling inward towards the Earth. In other words, it's not going to be at radius r anymore. And if you follow that logic all the way around, what you'll find is that, just like Kepler said, it will be in an elliptical orbit around Earth or whatever object it's in orbit around, but it won't be a circle anymore. So in this case, it initially starts falling closer to Earth. As it gets closer to Earth, it's speeding up because it's sort of being pulled towards the direction it's going all the way down here. So it's going faster here. So here it's going kind of too fast for the radius it's at, and it starts to get flung up farther away, and it ends up in an elliptical orbit. If you take a hammer and give it a whack in the direction it's going at this position, it would be going too fast for the radius it's at, and we would find something similar happens. It sort of overshoots and starts going farther away from Earth initially, and it ends up on another ellipse, which, causes it to go much farther away from Earth, but eventually it comes back to the same position. So the answer is, in that case, the object would follow an elliptical path. We're sort of experts now at finding properties of circular orbits, but this is what happens if you try to change that speed a little bit so it doesn't agree with the radius r for which we guaranteed this circular orbit. All right, next question. Again, object, we'll assume it's a mass m in a circle of radius r about an object of mass capital M, and the question we want to address now is how much time does it take to complete one complete circuit around that planet? That's called the period. Anytime you have something that's sort of repeating its motion over and over again, we usually call the period the amount of time it takes to do one complete circuit before it starts repeating again. So for a circular orbit, that's just how much time it takes to go around. And the symbol for that is capital T. T kind of for time, but we always use capital T if we're talking about the period. Again, what tools do we have to work with? And the answer is, well, if we're talking about a circular orbit, all we have to work with is v squared over r for uniform circular motion, and when we're doing some of the force x components, the only thing we have to work with is Newton's law of gravity, that gravitational force. So, same free body diagram. There's only one force on the object if it's in orbit around this planet. Here I didn't assume it's Earth, I'm just assuming it's some mass capital M. There's some gravitational force going in that way, and we always choose one of our axes along the direction of the known acceleration. It's centripetal in this case, that means toward the center of the circle. Okay, sum of the force x components equals max, same cancellation that happened before occurs here. And on the left-hand side, we're left with a gm over r. On the right-hand side, we have a v squared, but we don't want to know v this time. We want to know the period, and so I'm going to use the old distance over time trick here, and I didn't really write it out explicitly here, but this in parentheses here is our v, and I'm going to replace that v. Remember, we can calculate v as long as v is constant using any distance divided by the corresponding amount of time. And the time I'm interested in is the time that it takes to go around one complete revolution. So the corresponding distance it would go is one circumference, 2 pi r, where r is the radius of the orbit. Okay, all of that stuff's being squared, and now I'm just going to square it out, right? 2 squared is 4, pi squared is appearing here, r squared over t squared. I've just squared everything in this thing right here. And now looking at the equation that's left, just the left-hand side and the right-hand side, which are equal, I can solve for t. I'm going to do it a slightly different way and instead solve for t squared. Of course, one could easily take the square root of that and get a solution for what the period t is. The reason I left it in this form is to actually compare with Kepler's third law. Kepler's third law, which said something about the planet's orbital period, we called it t in that case, and its semi-major axis length a. And remember, in the special case where this object is in a circular orbit, the semi-major axis length a is just the radius r. Okay, so for a circular orbit, it says that r cubed over t squared is equal to a constant for everything that's in orbit around that particular object. And we're seeing exactly the same thing here. If you kind of, take everything that's multiplying r cubed and, divide it out onto the left-hand side and put the t squared in the denominator, we would have r cubed over t squared is equal to a number. And that number only depends on the mass of the object that things are in orbit around. So in the case of the solar system, that, our r cubed over t squared would only depend on the mass of the sun. So it's going to be the same for all objects that are in orbit around the sun, the same for every planet in the solar system. So that's just showing that one of the results from Kepler's Kepler's laws, the third law, can actually be derived from Newton's law of gravitation. And in this case, we can calculate exactly what that constant should be. For Kepler, that was something that was experimentally determined, and it seemed sort of miraculous that every planet in the solar system had this same constant when you took this crazy combination of its period and its radius or semi-major axis length. But this explains, at least in the circular orbit part of it, not all planets have very good, orbits that are approximated by circles, but it's not too bad of an approximation for most planets. Okay, 2 more things, I think, and then we'll be done with this chapter 5. Here's a question about a speed. A space shuttle releases a satellite in circular orbit 780 kilometers above Earth's surface. How fast must the shuttle be moving relative to Earth's center when the release occurs? And in this case, we're assuming the release is just a letting go. You're not going to give a push to the object. So we want to know how fast, essentially, this object has to be going to be moving around the Earth at a certain radius. The radius is a little bit tricky here because we're given the distance above Earth's surface, and it's also not in SI units, right? This was 780,000 meters, but that's above Earth's surface. If we want the radius of the orbit, we have to add on the radius of Earth to that 780,000 meters. So how fast does it need to go? Here I started from first principles. You could use that formula on the previous page, but it's just so simple to get. Again, here's our object of mass m. It's that satellite, and there's only one force on it, the force towards the center of Earth. And I'm going to choose that to be my plus x direction and do the sum of the forces x components equals max. There's only one force acting, and this is its x component. It's along the direction of plus x. So g times mass of Earth times the mass of the satellite divided by the radius of the orbit squared, where the radius is the radius of the circle that it's on, not this 780 kilometers. And that's equal to max, that's the mass of the thing in the free body diagram, the mass of the satellite, times v squared over r. And I did the same cancellations I did before. Solving for v, I get g times the mass of Earth divided by r, but I've got to remember that r is 780 times 1,000 meters plus the radius of Earth. I've got to put that in for the r that's in that final answer. And then I can calculate v in SI units. It's a rather large number. Things that are in orbit around Earth are usually going pretty fast, at least for orbits that are close to Earth. If we're really far away from Earth, that wouldn't be true, but objects at reasonable orbital distances are going thousands of meters per second. So that's why one of the reasons it takes a lot of energy to get something into orbit. Not only do you have to get it far away from the Earth, but you've got to get it going fast in the direction tangent to Earth. 7,460 meters per second. Okay, let's finish up with one voting question. Here is a comical picture of the side of Earth with Mount Everest shown here. Of course, Mount Everest is not nearly that tall compared to the radius of the Earth, but so that you could see it on the diagram, someone drew this cartoon that way. Suppose Earth had no atmosphere, so we could throw something into orbit without any air resistance slowing it down. And a ball were fired from the top of Mount Everest in a direction tangent to the ground. Okay, so we're firing it at just the right speed so that it goes into a low Earth orbit, at the same altitude as the top of Mount Everest. If the initial speed were high enough to cause the ball to travel in a circular trajectory around Earth, the ball's acceleration would be much less than g, approximately g, or it would depend on the ball's speed. So think about your vote. And the answer here is approximately g, and that's because, well, first of all, as I said, Mount Everest is the difference in the radius of the orbit at the top of Mount Everest and at sea level is almost nothing compared to the radius of the Earth. So you're essentially at the radius of the Earth away from the center of Earth. So the force isn't appreciably different. And therefore, if this object, if there's no atmosphere, the only force on it is the gravitational force. And even though it's going in a circle, it's still in free fall. And it's in free fall with the usual value of little g because we're not sufficiently far away from the Earth. I guess the reason I ask this question is because sometimes people might think, well, look, the object's not speeding up or slowing down, so its acceleration is 0. That's not true. The acceleration represents how fast the velocity vector is changing. And even though the magnitude of the velocity of this object isn't changing as it goes around, its direction is changing. And that means there's a substantial acceleration, the same acceleration that it would have if you just dropped the object and it fell straight toward Earth. Okay, that's the end of chapter 5.